Welcome to Domain 1, Section 1.12, Data Inventory and Management. In this session, we will cover the data foundations that every AI system stands on, how to inventory and catalog data, map how it flows, classify it, collect it responsibly, keep it high quality and balanced, deal with data scarcity, and document a model with a model card. Why does this matter beyond the exam? Almost every serious AI problem traces back to data, so mastering data management is how you prevent biased outputs, privacy breaches, and unreliable models. It gives you the vocabulary to question where training data came from, whether consent was obtained, and whether the data was even fit for the job. Let's begin with why data is so central. Conventional software runs on handwritten rules, but AI learns its behavior directly from data, which makes data quality fundamental. This connection is easy to see in hallucinations, where a system confidently produces false or nonsensical output. The usual culprits are training data that was biased, incomplete, mislabeled, or simply irrelevant. So, weak data quietly becomes weak intelligence. To manage data, you first need to know what you have, and that rests on a few building blocks. A data inventory is a list of your data assets. A data dictionary is that inventory at the level of a single application describing each data element. A business glossary sits above them, defining shared concepts so the same term means the same thing everywhere. And a data catalog ties it all together, holding the metadata, which is simply data about your data, like the label on a tin describing what is inside. When an organization has no central metadata repository, it still needs an inventory to run a privacy impact assessment, and a simple four-step cycle helps. First, plan, by setting the purpose and scope and deciding what counts as data. Second, decide, by choosing which attributes to record about each dataset, such as its owner, source, location, and usage rights. Third, populate, by gathering that information through data owners, interviews, surveys, or automated capture. And fourth, publish, by collating it into a spreadsheet or database while respecting how sensitive some entries are. Because data changes constantly, this cycle should repeat periodically, or after any major event like a merger. Once you know what data exists, you need to see how it moves, and that is the job of flow diagrams. A data flow diagram gives a high-level, horizontal view of data moving between systems, like a plumbing map showing water traveling from tank to tap. A usage diagram instead gives a vertical view, showing the detailed steps each procedure takes within a single application. The two are complementary, and adding swim lanes that separate teams or departments makes either one far more useful for managing privacy. Going deeper, data lineage traces data beyond its original system of record, following its sources, transformations, storage, usage, and the governance applied along the way. Think of tracing a river back to its spring. Lineage lets you find the true origin of a figure in a downstream report and pinpoint which application introduced a defect. Because it is huge and complex, Lineage is best handled with purpose-built tools, and you should start narrow, focusing on your most important applications and working upstream from there. Next comes classification, which sorts data into categories by shared traits, and data can carry several independent classifications at once. A single book, for instance, can be classified by genre, by language, and by age, suitability, all at the same time, and none of those determine the others. For AI, 3 classification lenses matter most. Critical data elements flag the data your most important processes depend on. Security levels typically run from public to internal to confidential to restricted, and they drive the controls applied. And sensitivity types, such as personal information or health information, may demand special handling, with the definition of sensitive varying widely between jurisdictions and legal regimes like the GDPR. Now to collecting data for AI. Organizations centralize data in warehouses or lakes so it can be analyzed and used for training, because models need large, verifiable volumes. A handy lens here is the 5 V's of big data. Volume is how much data there is. Velocity is how fast it arrives. Variety is how diverse it is. Veracity is how accurate and trustworthy it is. And value is what the organization can actually do with it. That data comes in 2 broad forms. Structured data is neatly organized in a predefined format, usually in a relational database with a clear schema, like a well-ruled spreadsheet. Unstructured data has no predefined shape, covering things like documents, images, audio, video, and social posts, and it makes up a huge share of what organizations hold, but is much harder to manage. Collecting data also carries 3 risks worth naming, and the first is consent. Internal corporate data can often be used for training, but data entrusted by customers usually needs consent based on the terms agreed when it was collected. And regulations like the GDPR require this. So organizations must confirm consent before training, involve privacy and legal stakeholders, and be able to remove someone's data from the training set if they withdraw permission. The second collection risk is fit for purpose, meaning the solution and its data must actually suit the goal. Warning signs include data that exists but cannot be easily accessed, data that lacks the right detail, volume, or quality, or a use case that regulation restricts as high risk. The third risk is data lag. Because models train on historical data over weeks or months, the world can move on, creating drift between what the model learned and current reality. You can counter this by retraining on fresh data, or by grounding the model's answers with up-to-date information at the moment of use, a technique known as Retrieval Augmented generation. Classification gets even trickier with AI specifically. The danger is a mismatch between the sensitivity of the training data and who is allowed to use the finished model. Consider proprietary source code, which is confidential and often blends with open source pieces, making it hard to separate the two. If a model meant for public use is trained on confidential data, that sensitive information can leak through the model, so the sensitivity of training data must always be aligned with users' rights to access it. Confidentiality must also hold across the entire development lifecycle, not just at the start. As data moves from its original source into a shared lake, onto exploration and training platforms, into specialized databases that store data as mathematical representations, and finally into the live production system, the access controls and protections from each stage can quietly get lost. The key is to make sure classification and handling rules travel with the data through every one of those stages. Data quality is paramount because a model is only ever as good as what it learned from, and quality is measured across 6 dimensions. Accuracy means the data is free of errors. Completeness means no required fields are missing. Consistency means formats are uniform across data sets. Timeliness means the data is current when needed. Validity means it follows defined business and technical rules. And uniqueness means there are no duplicate records. A related challenge is data balancing. If the training data overrepresents some groups and underrepresents others, the model produces skewed, biased results, much like a survey that only polled one neighborhood and then claimed to speak for a whole city. You address this early by profiling the data's distribution during collection, and by techniques like oversampling the rare cases, undersampling the common ones, or using algorithms that weight mistakes on the minority class more heavily. Closely linked is data scarcity, the surprisingly common situation where an organization has plenty of data but little it can actually use. The causes include quality problems, missing diverse or minority classes, a lack of consented or licensed data, data trapped in inaccessible systems, and a shortage of labeled data. 2 mitigations help. Augmentation, where you fill gaps with targeted real data or generate synthetic data that mimics the needed distribution. And model selection, where you choose a model that fits the amount of data you have to avoid overfitting. The final piece is the model card, which is a short document that travels with a model, like a nutrition label on food. It records the model's details, its intended use cases, its architecture, a summary of its training data, its performance metrics, its known limitations and biases, and its ethical considerations. Model cards build transparency and trust, and while ready-made templates exist, they often lack enough detail, so treat them as a floor rather than a ceiling. Let's bring it all together. AI rests entirely on data, so you inventory it with dictionaries, glossaries, and catalogues of metadata, and build inventories through a plan, decide, populate, and publish cycle. You map movement with flow and usage diagrams, and trace origins with lineage. You classify by criticality, security level, and sensitivity. Collect with attention to the 5 Vs: consent, fitness, and lag, and protect confidentiality across the whole life cycle. And you safeguard performance through data quality, balancing, scarcity, mitigation, and honest model cards. That was a big one. And you have earned a strong grasp of AI data management. Every important topic and idea from this session is covered in the multiple choice questions on RooCloud.com. Before you move on to the next session, work through the chapter-wise questions there, because they are the fastest way to lock down this much material. Practice first, and then move forward with confidence. Thank you for watching, and I will see you in the next episode.